Well, hello and welcome again to our journey into number theory, and we're going to start chapter 2, and this contains some elementary results on the distribution of prime numbers. Now, when we use the word elementary in mathematics does not mean easy. What it simply means is that we're going to use just bare hands methods to try and get some understanding about the distribution of primes, as opposed to using some higher level machinery, which we will do in later chapters. So I'm going to look here really going back and having a look at essentially the work of Chebyshev, and have a look at some of the ideas that we'll look at in more depth later, and also to see that doing things bare hands is a lot of hard work, and we need some more powerful machinery, that is of complex analysis and real analysis and some character theory, in order to properly understand or get some understanding of the distribution of prime numbers. So this chapter is going to be fairly technical in some sense, because we're just going to use simple ideas, but use them in a fairly, I think, clever way. So the oldest result concerning prime numbers is probably the fact that they increase without bound, that is, that there are infinitely many primes. And this result goes back to Euclid, and it's probably a proof that you've seen before, but it's worthwhile going through it again. And I'm going to, in fact, do 3 proofs, another one by Kummer, and then I'm going to give a constructive proof that there are infinitely many primes, and we'll see further proofs later on confirming this well-known fact. So Euclid's proof was by contradiction. And so Euclid says, well, suppose that there are not infinitely many primes, suppose there's only finitely many primes, then we can list them all, so I can put them all into a set, so there are only finitely many primes, P1 up to Pn, there are no others, according to my assumption, and I plonk them all into the set S. Euclid's idea then was to multiply all these primes together and add 1 to obtain this new number, capital N. And of course, if n is a prime, well, we have a contradiction because n doesn't belong to S. Otherwise, n has a prime factor q, but q doesn't belong to S either, because if I divide this number by any of the primes in here, the remainder's 1. And so q doesn't belong to S either, and so again we have a contradiction. It's a lovely little proof and goes back to the ancient Greeks, back to Euclid. Whether Euclid himself came up with this is not known, but it's recorded in his Elements. The second proof is by Kummer, and again we suppose not, and we let S be the set of all primes as above. So here's Kummer's proof of this. So same idea as before, we suppose we've got finitely many primes, P1 up to Pn, and we multiply them together, but we don't add or subtract 1 this time. And I call this number n, as in the previous proof. Kummer now says, well, n minus 1 is also a product of primes, and so it has at least one prime factor q. However, the GCD of 2 consecutive numbers is 1, and that means q can't be in this set, because the only factors of n are P1 up to Pn, and q and each of these are relatively prime, so q is not one of the elements of the set, and therefore again we have a contradiction. So it's a slight variation really on the proof given by Euclid. The third proof's a little bit more different, because this proof is going to in fact involve it's going to be a constructive proof. So we're actually going to not do it by contradiction, but I do it as follows. I take n1 to be any integer, any positive integer bigger than 1. Now this n1 has at least one prime factor. Could be n1 itself, but it has at least one prime factor I'll call q1. We then construct a number n2. I take my n1 and I multiply it by n1 plus 1. Now because the GCD again of these 2 consecutive numbers is 1, n2 has at least two prime factors. We know it's got prime factor q1 from the n1, and this number here must have another prime factor, which I'm going to call q2, and it can't be equal to q1 because these two numbers have no common factor except 1. Now I take the number n3, and I define that by taking n2 multiplied by n2 plus 1. Then this number also must have at least three prime factors, because n2 has factors q1, q2, and there must be another prime factor dividing n2 plus 1. And you continue this process as often as you please, and that therefore enables us to construct infinitely many primes. So that's an interesting proof, slightly different in flavour to the other two proofs. So this one is in fact constructive. You can explicitly write down any number of primes you like. So if you wanted 1,000 distinct primes, then you could use this method to do it. So little bit of notation. I'm going to let Pn denote the nth prime. So P1 is 2, P2 is 3, P4 is 5, and so on. Sadly, one earlier book on number theory, I think by Lamer, who gives a list of all the primes, he actually starts counting the primes at 1. Well, we don't take 1 as a prime. The primes start at 2. 2 is the only even prime, so P1 is 2, and so on. And I'm going to let pi of n, this is a function we're going to study in great detail later, but pi of n denote the number of primes less or equal to n. And trying to understand this function and understand its asymptotics was a major problem in number theory, which was, well, partially solved when we got the prime number theorem itself, which we'll have a look at in a much later chapter. So that means then that if pk is n, that means if the kth prime is n, then the number of primes less or equal to n is k. And if the nth prime, the number of primes less or equal to n is k, then the kth prime must be less or equal to, well, not necessarily equal to, but less or equal to n. So in the case of P10, for example, then is 29, and in fact P of 29 is in fact 10. So I'll leave you to check. You should make up a list of primes and check that the 10th one is in fact 29. Now from Euclid's proof, we can easily deduce that the nth prime must be less or equal to the product of the primes before it plus 1. That follows pretty easily from the Euclid's proof that we went through above. So the nth prime has to be less or equal to the product of these two, plus 1. Now, using this observation, we can get a bound, not a very good bound, but we can get, we've got to start somewhere, we can get a bound on the nth prime. And we're going to show that the nth prime is less or equal to 2 to the 2 to the n minus 1. So we have nested indices here, 2 to the 2 to the n minus 1 for n bigger or equal to 1. And we're going to prove this one by induction. And so I'll go through the little proof of this by induction. Firstly, if we let, so that's what we're trying to prove, the nth prime is less or equal to 2 to the 2 to the n minus 1 for n bigger or equal to 1. So if we put n is equal to 1 into here, then this just collapses down to 2, and of course the first prime is 2, so the result is certainly true for n equals 1. And so in fact you can get equality, in fact, only in this first situation here. Now, by inductive assumption, I'm going to suppose then that the kth prime is less or equal to 2 to the 2 to the k minus 1, and I'm going to use strong induction, so I'm going to suppose this is true for all k less or equal to n minus 1. So I'm going to assume the kth prime is less than this for k equals 1, 2, 3, all the way up to n minus 1. And I'm going to then show it's true also for n. Now, you can almost perhaps see how the proof's going to go. I'm going to use this result, this thing from Euclid. So by Euclid, the nth prime is less than the product of all the primes below it plus 1. And now by my assumption I can replace each of these with, perhaps I should write less or equal to here. This is 2 to the 2 to the 0, 2 to the 2 to the 1, up to 2 to the 2 to the n minus 1. That was by my inductive assumption, because we assumed these, the result was true for all the numbers up to n minus 1. And then we just simplify the indices here. We get this nice simple geometric series. And you can sum that geometric series very quickly and easily. I'll leave you to check. When you sum that, you just get 2 to the n minus 1 minus 1. So that's a little geometric series in there to sum. And now you can just check with a little side calculation that 2 to the 2 to the n minus 1 minus 1 plus 1 is less than this one. And that's fairly easy to do. You can just check by taking this and dividing it by that and show the answer is less than 1, and that'll get you this fact here. So this is for n bigger or equal to 1, and so we've now shown that result then, so Pn is, if it's true all the way up to n minus 1, then it's also true for n. And therefore the result is true for all n bigger or equal to 1 by strong induction. So that gets us this little inequality here, but it's pretty weak because these numbers grow very, very quickly, much bigger than the primes do. But at least it gives us something. It gives us an upper bound on the nth prime, and from that we can see what else we can deduce. So as a corollary to this, we can show that the pi of x, we can get a lower bound on pi of x, that the number of primes less or equal to x has to be at least log of x on log 2. Now again, as we'll see, this is not a particularly useful, lower bound on pi of x, but it actually tells us two things. Firstly, we're going to see a connection, a much more explicit connection between pi of x and log x coming up later. And so we're going to see that this log function, as Gauss realized, plays a very important role in the study of pi of x. This is actually log of x. Secondly, it also shows us, because this function goes to infinity, as x goes to infinity, this gives us yet another proof that there are infinitely many primes, because pi of x is bigger than something which becomes arbitrarily large. It does so very slowly. Log of x doesn't grow very quickly, but it does in the limit go to infinity. So the proof of that is just going to use the result we just had before on P of n. So that's the result we're going to prove, that pi of x is bigger or equal to log of x on log 2. Now, by the way, when I write log, I of course referring to logs to the base e, unless otherwise specified. So I'm going to choose an x that lies between 2 to the 2 to the n minus 1 and 2 to the 2 to the n. And that means then, and we know that P of n is less or equal to 2 to the 2 to the n minus 1. That was our previous result. And that then means if P of n is less or equal to that, then pi of x is bigger or equal to this n from our remarks before. So I need to get my hands on this n. Now what do we know? We know that x is less or equal to 2 to the 2 to the n. And so I can recover the n by simply taking logs to the base 2 twice. So I can rewrite this as n as log of x to the log of x all to the base 2. So we can then simplify this. In fact, I probably should write n equals this at the moment. So I'm going to change base. So I'm going to change from base 2 to base e. And so you can use the change of base formula to get the log of x on log 2 over log 2. These are all now to the base e. So I've used the change of base formula twice there. I can use the log laws on the top to simply rewrite it like that. Now the log of 2 is negative 0.336 approximately, So I can write this as bigger or equal to that, and then I'll toss that away and just say it's bigger or equal to this. So log of x on log 2, that should be there. So that means then, now that was my n, so we found a formula for n, and we found pi of x was bigger or equal to n, and so we conclude that pi of x is bigger or equal to log of x on log 2. Now that particular lower bound is not particularly useful because as we'll see, well, it does, as I said, tell us two things. It tells us we should be thinking about logarithms when we're thinking about pi of x, and it also gives us another proof there are infinitely many primes, but as a bound it's rather poor. For example, if I look at pi of 10 to the 9th, that is, how many primes are there less than 10 to the 9th? Well, there has to be bigger than this number, but that's about 4. Well, it's no big surprise that there are more than 4 primes between 0 and 10 to the 9th, so it's not a particularly useful bound, but we have to start somewhere with this, and at the moment just using simple bare hands techniques, that's all we can get. We'll do a little bit better shortly. Just to have a look at how do primes and squares compare. Well, there are infinitely many, of course, of both, but when you take the reciprocals of the squares, then you get pi squared on 6, which is finite. So although there are infinitely many squares, the sum of their reciprocals, they thin out fairly quickly because the sum of the reciprocals is finite. It's pi squared on 6. So in some sense there are not too many squares. On the other hand, if I look at 1 over Pn, the nth prime, and take this sum, does this converge? Well, we're going to see no, that it doesn't. I'm going to prove that this diverges. And so in some sense there are more primes than there are squares. It's interesting to note that if we take the above sum over all known primes, then this sum in fact is relatively small, even though I'm going to prove that it diverges to infinity, which perhaps is an interesting statement really about how much we really know about the primes. If we take the sum over all known primes, the answer is small, even though the sum diverges to infinity. Now before we have a look at that, I want to introduce one of the most important facts in analytic number theory, and this is the Euler product. The Euler product. And so Euler first came up with this. Euler loved playing with infinite series and products, and ignoring problems of convergence for the moment, you can yell in a moment about convergence issues, but just for the moment, imagine if I took I expanded out these brackets. So I take 1 plus a half, 1 on 2 squared, 1 on 2 cubed, and so on. 1 on 3, 1 on 3 squared, and so on. 1 on 5, 1 on 5 squared, then 1 on 7, not 1 on 9, 1 on 11. So I'm taking these numbers here are the prime numbers. So I'm taking these geometric series of the reciprocal powers of the reciprocals of the prime numbers. In product notation, that simply means I'm taking 1 plus 1 over p plus 1 over p squared forever. Take a product over all the primes. Well, what's going to happen if I expand all this out? Well, on the one hand, we can sum this series in here, because this is just a geometric series, and so I can sum this and obtain this sum 1 plus p turns into, of course, 1 minus 1 over p to the minus 1. It's just a geometric series. And so I can write this product then as the product of p prime, 1 minus 1 over p to the minus 1. On the other hand, if we come back to this product here, if we expand this, take a deep breath and expand all this out, well, you'll get 1 times 1 times 1, so you get a 1. You'll get a half, and you take 1 small the brackets. You'll get a third, you get 1 small the other brackets. You'll get a quarter, 1's in all the other brackets. You'll get a fifth. You'll get a sixth if you take those two together. and 1s from all the other brackets, 7th, 8th, 9th, 10 by taking these two together. And you see you're going to get every integer by unique factorisation. You'll get every integer exactly once in that sum. So, on the one hand, we've seen that the product can be written like this. On the other hand, because Euler noted, because of unique factorisation, the expansion on the left-hand side produces the reciprocal of every positive integer exactly once. In other words, we can write this down. And well, now you can start to scream, because you will say, but hang on, this is all nonsense, because this infinite series here diverges, and so you've written down infinity equals infinity. This is not good mathematics, and I quite agree, but it just purely symbolically, that's what's happening. However, this equation, which I put in inverted commas, is really trying to say something very important, because what I can do now is I can replace the p with p to some power, p to the s, where s is bigger than 1. And if you do exactly the same calculations as I've just done, in a rather dodgy way, but if you do the same calculations now with p replaced with p to the s, then you get this famous identity here, which is called the Euler product, and this is valid provided s is bigger than 1. So this gives us an amazing connection between the primes and this strange looking infinite series here. And this function, if we think of s as a variable, this function is denoted by zeta of s, and it is of course the famous Riemann zeta function. And it plays an absolutely central role in analytic number theory. Everything boils down to studying this function here, and we will do that in some detail in a later chapter. This is the famous Riemann zeta function. Euler examined this. He noted that if, for example, if s is 2, we get pi squared on 6, and we'll see that if s is an even number, then you can sum this explicitly. And if it's an odd number, then we don't really know a lot, in fact. So we will study this function in much detail later on. For the moment, I'm just going to observe that if you chop off this product here up to pi of n, then you'll get the sum of the reciprocals up to some particular point. I haven't said where you'll go up to, but you'll get it up to some particular point, and that's simply, of course, bigger than 1 plus a half up to 1 on n. Now, in the next video, we're going to examine in detail this sum 1 over p less or equal to x. That is, we're going to look at this, and p prime. So we're going to have a look at the sum of the reciprocals of the primes, and we're going to show that this sum diverges as x goes to infinity.